Video number 9, we talk about difference amplifiers. It's like a simplified version with difference amplifiers. So in this video, 11, let's talk about a more generic form of difference amplifiers, or also the implication of difference amplifiers. Okay. So we have a amplifier like this. So we have resistor input, feedback resistor goes in. So we have V plus. The input goes to non-inverting input. V minus. The input goes to the inverting input. We call R1, R2, R3, R4. And video number 9, we talk about situation when we have a zero voltage here. So R4 is connected to zero, to connect to the ground. Okay, and in actually most common case, this will not in the ground. You will go to a virtual ground or reference voltage. We call that VR. So, and similarly, we can derive the difference amplifier equation for the VR. I think we can just repeat a little bit in here. Now, the quicker way I used to do is forget this part. Okay, forget R3, R4, all this here. Just assume this node have a voltage we call VC. For center voltage, we call that VC. You can call it any number, any parameters, but I call that ABC. Okay, this equivalent, we have a circuitry like so like this. V out and with a VC and V minus R1, R2. That's the inverting input here. Okay, the quicker way we normally do is we just reference everything relative to VC. Okay, so we have V minus VC for the input, V out minus VC, and VC minus VC here turn into 0 volts. Okay, now this turn into a typical non-inverting amplifiers we all know, right? So we can write out the V out voltage, which is V out, right here, V out minus VC equals minus R2, R1, V minus VC. Okay, so we can start from here, and we know V out equals minus R2, R1, V minus plus R2, R1, VC, and plus VC. Okay, we distribute this into the bracket here and move the VC from this side to the other side. And the V out, we can combine this R2, R1, V minus plus 1 plus R2, R1, VC. Here's R1. Okay. Now let's take care of, we already take care of this part. So now we take care of the VC part. What is VC? Okay. So VC we could draw it in different ways. We have here, if you look back to the diagram, we have V plus, and it goes through a resistor R3 and another resistor R4, then go to VR. Okay, then the middle point here is VC. Okay, so this is right here, and now we just figured out what's VC, and this is just a voltage divider, a little bit fancier ways because we have a VR rather than a zero ground, and there's many ways to write this, and just we talk about the regular ways first. Okay, we look the current goes through this voltage divider, then we use the current multiplied by R4, then give you the voltage of these sections, the voltage potential here, then we plus VR, then we VC. So VC equals to V plus minus VR. It's voltage difference divided by R3 plus R4. It's a current flows through the circuitry, and times R4 and plus VR. That's the VC. Okay, so we can arrange this in a little bit different ways. This can turn into V plus times R4, R3 plus R4 minus VR, R4, R3 plus R4 plus VR, and this VC equals to what? Okay, R4, R3 plus R4, V plus, and minus VR 1 minus R4 R3 plus R4. Okay, so VC equals R4 R3 plus R4 times V plus plus this 1 minus this section here. We can turn that, will turn into R3 plus R4 times VR. Okay, so this is the VC values. Okay, another quick way to write this figure out what VC is. It's different ways. I'll just erase everything here. And so what we can assume is if it's no VR, okay, VR is equals 0 volts, is no VR, then VC, we call that VC1 equals 2V plus divided by R3 plus R4 times R4. This is a typical voltage divider, everybody know that. Okay, then another situation we can think about is VRs exist and V plus is equals 0. Okay, so the current will flow that direction. So we have VC2 equals to VR divided by R3 plus R4 times R3. Okay, because here it's 0. Okay, then we can combine these two, VC1 plus VC2. Let's give you the VC equals VC1 plus VC2. If you look carefully, this is exactly the same formulas. Okay, so there's many ways to figure this out. But once we know the VC, we can plug the VC back to the equation here. Okay, so we have V out equals minus R2 R1 V plus V minus plus 1 R2 R1 this whole thing here, R4 R3 plus R4 V plus, and the plus R3 plus R4 VR. Okay, this is a full equation for this circuit up to here. Okay, it looks like a whole lot of stuff and just really scary, but you know, we can make some assumptions, really simplify this. Okay, what's the assumption we normally make? We make this assumption is R2 R1 ratio, R2 R1 equal to R4 R3 ratio. Okay, if we assume R2 R1 the ratio equals to R4 R3. Okay, now we can replace all R4 R3 by R2 R1 ratio. Okay, before that, let's further simplify this equation. Go down here, we have V out minus R2 R1 V minus plus 1 plus R2 R1, then we divide by R4 here, so we get R3 R4 plus 1 and V plus, and this side we divide everything by R3. We got 1 plus R4 R3 VR. Okay, now we use this substitution here. So we replace all the R3 R4 with R2 R1. So we got V out equals minus R2 R1 V plus V minus plus 1 plus R2 R1, and here is 1, R3 R4 is R1 R2, right? So it's R1 R2 plus 1 V plus 1 plus R4 R3 is R2 R1 R2 R1 V R. Okay, let's simplify this again. V out equals minus R2 R1 V minus plus 1 plus R2 R1, and here we multiply R2 both the top and bottom, so we got R2 R1 plus R2 V plus, and by same token we multiply R1 both the top and bottom, so we got R1 R2 R1 V R. Okay, and this we know that is this charge is equivalent to R1 plus R2. Okay, now what we can say is if we multiply this into here and multiply this into here, minus R2 R1 V minus, and R2 R1 here is cancelled with that, so what will be left over is R2 R1 V plus, and this is invert, this was the invert of that, everything is cancelled, so we just turn it to VR. This looks very simple now. Now V out equals, we move the R2 R1 to the R2 R1 to the outside, so R2 R1 V plus minus V minus plus VR. Okay, this looks very simple now. If you remember from the video number 9, you can tell this part, just the equation when V R equal to 0. Okay, and what this really means, this means V out minus VR equals R2 R1 V plus minus V minus. Okay, it's just, you know, one equation, two forms. And the only, whenever you go back to these plots, the only difference when you add a virtual ground or reference voltage to this node is the output now is with respect to this voltage VR. Okay, with respect to reference voltage, and the rest are just the same. Okay, and this is just, if you have both input V plus V minus, you just take the difference between the V plus and V minus. So you take the difference between the two inputs, then just remove the common mode voltage of the input, and you set a new common mode voltage VR. Okay, this is very common, very useful when you do level shifting or those calculations. Another way, so let's summarize here. We got 3 application major. First is a difference amplifiers, right? You take the difference between two inputs and remove the common mode voltage. Okay, on the input side, then you add another virtual ground or reference voltage to the output. And another application is whenever you can set either V plus or V minus to 0. Okay, if we set V minus equal to 0, that's basically what means in this circuitry you can just wire this to ground. Okay, if V minus equal to 0, the equation turns into V out R2 R1 V plus plus VR. Okay, this is linear equations, and you just amplify or attenuates a signal, whatever signal or the input, and level shift by VR. Okay, and in another situations you can use V plus, you set V plus to 0. Okay, and V out equals what? Equals minus R2 R1 V minus plus VR. Okay, this is just a non-inverting format of this non-inverting format, right? The inverting format, you have a negative slope. You still can amplify the signal, attenuate the signal, then plus a level shifting. So basically, with this one simple circuitry, one op amp with 4 resistors, by using different ratios, different resistors, and you can implement whole bunch of linear calculations. Okay, so in the next video, I think I will give you a real life examples how this actually works when you interface with ADCs. So the next video will talk about how we use this circuitry to interface ADC.